Section 1. Preface. Why this paper matters now. If you've ever watched a modern ML system confidently recognize objects in an image, but then stumble on a simple relational question, like, is the red cube the same size as the blue sphere? You've felt the gap this paper tackles. Today's models are excellent at perception and pattern recognition, yet they often struggle with reasoning about relationships among entities. As LLMs and multimodal systems move into more complex planning, tool use, and scientific or physical domains, we need modules that make relational reasoning a first-class operation, not an emergent byproduct. This paper proposes a simple, plug-and-play neural module, the Relation Network, that does exactly that and shows it working across vision, language, and physics. It's a foundational idea that anticipates the current wave of graph and relation-centric architectures in ML. Title and authors, context in the field. The paper is A Simple Neural Network Module for Relational Reasoning by Adam Santoro, David Raposo, David Barrett, Mateusz Malinowski, Razvan Pascanu, Peter Battaglia, and Timothy Lillicrap at DeepMind 2017. It sits at a pivotal moment when VQA, visual question answering, benchmarks were exposing the limits of attention-based CNN plus LSTM stacks on relational tasks, and when graph and interaction networks were emerging for structured domains. This paper's contribution is not a heavy domain-specific system. It's a small, reusable module designed to explicitly compute relations that you can drop into existing pipelines. Abstract. Key claims and results rewritten for spoken explanation. The authors introduce relation networks, RNs, a simple neural block engineered to compute relationships among objects in an input. They plug RNs into end-to-end architectures and evaluate across 3 domains. Cleaver, visual question answering, they reach state-of-the-art, surpassing human performance, particularly on the relational categories where prior models struggled. Babby, text QA, they solve 18 out of 20 tasks when trained jointly, competitive with memory-augmented baselines. Dynamic physical systems, they infer hidden connections and count connected subsystems from motion and show transfer to motion capture data. They also build sort of Cleaver to isolate relational versus non-relational questions and show that strong CNN plus MLP models don't automatically acquire relational reasoning. Adding an RN lets them do so. The takeaway, an RN-equipped architecture can discover entities and reason about their relations from raw inputs without explicit object supervision. Introduction, problem framing and motivation. Relational reasoning, thinking about how entities relate, is central to intelligence. Classic symbolic systems make relations explicit, but they suffer from brittle generalization and the symbol grounding problem. Deep learning, conversely, grounds representations in data and scales well, but often struggles when the structure is sparse and reasoning depends on a few precise relations. This paper points out a simple truth. Powerful CNNs and MLPs are not naturally good at certain relational inferences. Tasks like count the objects left of the red sphere require comparing and composing attributes across multiple entities. Many deep models treat the entire input as one big vector and leave that relational work implicit. The authors propose relation networks to explicitly compute pairwise relations over sets of objects, and then show this solves the kinds of questions that trip up end-to-end CNN plus LSTM pipelines. Model, method, core approach. The RN's core idea is as follows. Treat the input as a set of objects, consider all unordered pairs of those objects, compute a shared relation function on each pair, and aggregate those relational outputs to produce an answer. Objects. The inputs are converted into a set. In images, cells of a CNN feature map are treated as object candidates. In text, each sentence becomes an object. In physics, each entity at a time sequence is a row in a state matrix, an object. Relation function, G. A small MLP processes each object pair. Critically, the same G is used for all pairs. That makes it data efficient and encourages generalization. G learns what relations look like, not how a particular pair behaves. Aggregation, sum across all pairs. This makes the module invariant to the ordering of objects and distills all relational evidence for downstream decision-making. Output function, F. Another small MLP takes the aggregated relational signal and produces the final answer, such as a class label or count. Conditioning on the question. For QA tasks, they feed the question embedding into G, so the RN computes relations relevant to the query. For example, the question, "Is the cube the same material as the cylinder?" pushes G to focus on material comparisons among those shapes. Why these design choices matter. All pairs coverage ensures no potentially relevant relation is missed when you don't know a priori which relations matter. Weight sharing in G is the key to data efficiency and generalization. Instead of the network learning many separate relational subfunctions, it learns one that applies broadly. Summation makes the module operate on sets properly. Order invariance is a must for relational reasoning over objects. Keeping CNNs and LSTMs as upstream processors lets the RN induce object-like features even when the inputs are unstructured, avoiding brittle hand-engineered object detection. Experiments, zero-shot transfer. What the experiment tests conceptually. Can a relation function learned in one setting generalize to a structurally different domain without task-specific fine-tuning? In other words, is the RN learning relations in a way that's invariant to surface details? Setup and why it's interesting. Dynamic physical systems. Balls move on a table. Some are connected via invisible springs or rigid links. Tasks include infer which pairs are connected and count how many connected subsystems exist. They report that learning relations here transfers to unseen motion capture data, predicting connections among human body joints during walking without retraining on mocap. Valid conclusions versus overstated. Valid. The RN's pairwise relational inductive bias generalizes well across domains when the relational structure is similar. For example, connectivity inferred from correlated motion. This is a form of structural transfer. The what relation looks like concept applies beyond the original data. Overstated would be claiming broad zero-shot transfer across arbitrary domains. The reported transfer remains within the logic of inferring links from dynamics. Influence on system design. If your application involves latent relational structure, social ties, causal links, physical constraints, learn a shared relation function and keep it separate from perception. You'll get better cross-domain robustness than trying to bake everything into a single monolithic network. Experiments, few-shot learning. What the experiment is testing conceptually. While the paper doesn't run explicit few-shot benchmarks, it probes data efficiency indirectly by sharing the relation function across all pairs. The question is, does this architectural sharing reduce the number of examples needed to learn relational patterns? Setup and why it's non-obvious. In Cleaver and sort of Cleaver, the RN applies the same G to thousands of pair instances per image. Each training example yields many relational training signals. Valid conclusions versus overstated. Valid. The RN is data efficient for relation learning because a single G sees many pairwise instantiations, accelerating learning of the shape of a relation. The authors also note small models perform best, suggesting the inductive bias carries more weight than sheer capacity. Overstated would be claiming few-shot mastery. There's no controlled few-shot experiment in the paper. It's fair to infer increased sample efficiency for learning relations, but not to generalize to classic few-shot regimes without evidence. Influence on system design. If you need robust relational reasoning and have limited data, use a shared relation module. You'll get many effective training samples per input because each object set generates many pairs. This is a practical way to stretch training signal without changing your dataset. Experiments, representation learning. What the experiment is testing conceptually. Can the RN induce upstream networks to produce useful object-like representations even when the pipeline isn't told what an object is? Setup and why it's interesting. In images, they treat each CNN feature map with location tags as an object. There's no object detector. In text, they treat sentences as objects. In physics, rows of a state matrix are objects. The RN then operates over these sets. Valid conclusions versus overstated. Valid. The end-to-end training causes the CNN and LSTM encoders to shape their outputs into embeddings that serve as objects for relational computation. Performance on Cleaver, especially relational categories, implies these emergent object representations are effective. Overstated would be claiming explicit interpretability or consistent object segmentation. The paper doesn't visualize learned objects or prove objecthood beyond functional usefulness. Influence on system design. You don't need perfect object detection to get relational reasoning off the ground. Treat feature cells or sentences as objects and let the RN's gradient pressure shape upstream representations. It's a strong argument for modular training where reasoning shapes perception. Model versus human and strong baselines. Cleaver from pixels. RN augmented model reaches 95.5% overall, surpassing the best prior general VQA models by a large margin, and exceeding reported human performance, around 92%. The jump is most pronounced on relational categories, like compare attribute and count, where attention-based CNN plus LSTM models lagged near simple baselines. Cleaver from state descriptions, 96.4% accuracy, using structured object matrices, showing the RN is agnostic to input form. Sort of Cleaver, CNN plus RN gets 94% on both.